All right, so this is the electric vehicle speed controller design project for the MAE 318 lab. My name is Ryan Benham.
I'm Rylan Ramsey.
I'm Preston Guthrie.
As you can see, we've got our favorite type of dog as a background. Um, so this is basically just who we are and what we're solving. So for our lab, the objective throughout the semester is to understand like electric vehicle speed control systems, model the electrical and mechanical components, design through simulation, and then just test and iterate. And then we used MATLAB and Arduino, so a lot of those skills had gotten better throughout the semester. And in a team environment, we needed to collaborate. And at the end of the day, we are pitching this idea, so it's kind of an entrepreneurial mindset. It's kind of an entrepreneurial project to please the customer. And speaking of the customer, so we want to explore speed control algorithms, achieve precise and reliable speed control for our customer, and we want to enable the vehicle to reach desired speeds. Um, Also, we're testing out or like a variety of different control systems and prototypes, and through this we can offer a multitude of solutions, but more importantly, we came up with the best solution possible after all of our research. And through this, we kind of had like an iterative process. So in lab one, we developed a model of the electrical and mechanical system. We were able to find a few parameters, so like beta, beta naught, and KT. And then in lab two, um, we are actually we modeled the system again. This time we found K, DC, and tau. And the result of this was, finding the variables in a differential equation that allowed us to find the relationship between uh, the voltage applied to the motor and the DAC value. And we were able to develop a system step response from this. In lab three, we used these same parameters in the other two labs, and we were able to create an experimental versus theoretical Bode plot. This let us see how well our system was actually being modeled. And then also we were um, able to come up with like a proportional controller to achieve desired disk speed, and then different gain values were tested through this. And in lab four, we were actually able to come up with a PD controller. This is the first type of controller that we were testing. Um, for this filter, we tested a low pass filter, and it actually had a positive effect on the gain of the system. And then we also modeled a PI controller, which, as you might know, is a proportional integral controller, and it performed the closest to the theoretical response. It was able to achieve the desired velocity. And then in lab five, we were able to come up with our final design to meet all the customer expectations and like the criteria for this project. And we found that a PID controller was best suited for this. It had a short duration of overshoot, fast settling time, and a fast response time.
The controller we ultimately went with was the PID controller, which we tuned using MATLAB's SISO tool. The trade-offs for this design are initially high voltage, and it requires a low-pass filter. Some of the assumptions we made in this controller was that the plant transfer function can be represented by KDC over 1 plus tau s, and we modeled wind and friction conditions using a constant voltage disturbance. Some of the client specifications we used were zero steady-state error, less than 20% overshoot, over 0.1 second rise time, and less than 0.2 second settling time.
All right, and then so the customer may want different types of controllers. So we've listed out three different types. The first is a proportional integral, which will ensure zero steady state error. It's simple to use and tune, and it's not sensitive to noise because it lacks the derivative portion. But it's pretty slow compared to the other two, and it can have a bit of overshoot. Uh, and the best use cases for the proportional integral is that for slow, stable systems, noisy systems, and like simple systems that you want to be reliable. The next controller type is the proportional derivative, and this is a faster controller usually, and it has damping, which means it'll have less overshoot and it'll kind of remedy the oscillation from the overshoot. Uh, it does struggle with reaching a steady state of zero, and it's sensitive to noise, which, as mentioned before by Ryland, is we will need a low pass filter for that. But the best use case for this is speed and stability. And then the last controller, which we settled on, was the PID controller, proportional integral derivative. And it's a combination of the last two. And it's optimal because it has a fast response time. It still has the damping from the derivative controller. And it still reaches the zero steady state error. It still has the issue with noise, but that can still be fixed with the low pass filter. And the biggest con is that it's just complex to tune because there's three different gain variables that you have to design for. And this is best to use for tight specifications, which is what we had with the customer, and also just a middle ground, which is what we also had. And that's why we settled with the PAD.
And so overall, we learned a lot from this experiment, and a lot of things we realized could be applied to other applications. And so some of the things that we thought of were like a smart conveyor belt with a sorting mechanism Using the, speed control skills that we've learned, we thought that we might be able to use a DC motor to run a conveyor belt and then somehow use some sort of imaging processing to identify objects and then control a sorting arm. This is useful in manufacturing because it automates a lot of simple tasks and it can just overall speed up the process. Another idea, this is kind of close to what we came up with, or I guess, it has that EV sense, but a little delivery robot. This is closely related to what we did, but we could use two motors to power like a two-wheel drive, or even one motor, two-wheel drive robot that is used to deliver, packages or even food. And it can navigate its way two different waypoints, which are defined in MATLAB. Like you can, tell it different path instructions and stuff. It could be, useful, especially one thing we thought of was like, people with disabilities, they might not be able to get up from, wherever they're at and go achieve something without having to, ask someone for help. But if they had something like this robot, they would be able to, get a water from their kitchen or, just pick up certain things or, be able to help them out. Another idea was regenerative braking, which is kind of the opposite of what we did. In the lab, we found out that if you manually spin the motor by hand, it will generate a voltage. So this led us to think that maybe we could use this to charge a capacitor of some sort, which will then be used to recharge a battery. Why is this useful? It iterates and improves on current EV technology, and the capacitor is needed so that you can have a constant voltage being applied to the battery. It's not going to shock it with any sort of currents. So, and yeah, that's basically it. Sums up everything for our project. We hope that you enjoyed our presentation. Thank you.